Today I want to talk about the ideal gas law, which is one of those concepts that people usually retain when they take a chemistry class. I was talking to our physics instructor the other day, and he was saying that we were talking about what we were teaching, and I was talking about the gas laws, and he goes, oh yeah, PV equals nRT. That's what they remember from chemistry, PIV nRT, or the ideal gas law. So this is really a combination of all of the different gas laws. If you've had the opportunity to review some of my other videos, you will have seen about Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. And when you put them all together, then you end up with this relationship between these variables for gases that we call the ideal gas law, or PIV nRT, or PV equals nRT, where P is your pressure. Now the SI unit for pressure is pascals, but the pressure can have variable units. And we'll kind of get into that in just a second when we talk about the universal gas constant, which is the R part. Now the volume, V, is going to have units of liters. That's important. So if you're given a quantity that's not in liters, so if you're given a gallon of something, a gallon of a gas, for example, then you are going to have to convert to liters in order to use this equation. N is the number of particles, so that's going to be in moles, because that's what we as chemists use to talk about quantities of things. It answers kind of the how much or how many question. Now R, I'm going to bring over here, is the universal gas constant. And the universal gas constant is just a way that when you put together these variables, they are all related in a specific way. And when you do enough experimentation, then the value that shakes out when you rearrange this is R. And R is usually given in a number of different units in order to accommodate these variable pressure units. So the two that I usually give my students are an R with atmospheres in it, which is 0.0821, and the units on that are liters times atmospheres over moles, moles times Kelvin. Liter atmospheres over mole Kelvin. So that's the unit on it. That entire thing is the unit. It actually comes from 0.8206. So sometimes you see it rounded like this, sometimes you see it in its longer form. And then the other R version I usually give is this one, 8.3145, and that is because it is in kilopascals. So the units on it are liter kilopascal per mole Kelvin. You will find entire listings of R's, so you can have an entire listing of universal gas constants for the different pressure units. So you could have one in torr, have one in bar, millimeters of mercury would be the same as torr, but you'd have all these different values that are all the same. It's still a constant, but because they have the different pressure units in them, then it's going to be a slightly different number value, even though the math will still all shake out okay. So it really depends on what pressure units you're given or what pressure units you're looking for. And then temperature here is your absolute temperature, which means that it's in Kelvin. So if you're given a temperature that's in Fahrenheit or Celsius, then you're going to have to convert in order to get it to Kelvin. So PV equals nRT. Now the reason that the units are important, well, units are always important because we're scientists, but the reason that the units have to be so specific for each quantity is because of the units on the R values. You have to have them correspond in order for the units to divide out correctly to give you the units that you're looking for when you solve problems. So let's look at an example. Let's take an ideal gas with a pressure of 98.6 kilopascals, a temperature of 32 degrees Celsius, in a 52.5 milliliter container, and it wants to know the number of moles of gas particles. So we're given a whole bunch of different things. So here's PV equals nRT. There's a couple triggers that would trigger a PIV nRT problem. One is anything to do with an ideal gas, and we'll talk about that in a little more detail in just a minute. But the other thing is that I'm not changing any one of the variables. I'm given all of the variables, but I didn't say anything about changing the temperature or changing the volume or changing the pressure. It gave me information about all of those and asked about a different one. So to me, that triggers PIV-nRT, as opposed to one of the other gas laws like Boyle's law or Charles' law, where it says, I changed the condition, what happens to the other one? That's not what you see here in this problem. So this is going to trigger PIV-nRT. So what I like to do is to list out my variables. So my P is given in kilopascals, which I can keep. I just have to use the correct R then, so I'll list that one out next. The R is going to have kilopascals in it to match the kilopascals that I'm given, so I'm going to use this one, 8.3145 liter kilopascals per mole Kelvin. I'm also given a temperature in degrees Celsius, so my T here is 32. I'm going to have to convert that to Kelvin. My magic number there is 273.15, but because I have a ones place here, we're going to have to round this thing anyway, so I'm just going to add it there, which gives us 305 Kelvin. And the last bit is the volume, so I'm given 52.5 milliliters. Now that value, in order to divide out the liters in my R value, is going to have to be converted to liters. So we know that there's 1,000 milliliters in 1 liter, because we know our metric conversions. So when you divide that out, you end up with, and you can kind of write this however you want. I like writing in scientific notation, because I'm a scientist. And then what's missing then is the how many moles. So what I'm searching for is my N. Now that I've listed out all my variables, I can kind of look at my equation and rearrange it to solve for the variable that I'm missing. So I'm solving for N here. N is equal to PV over RT. So then I can plug in my values that I've now converted or been given, times my volume, divided by my R, which is the constant, times my temperature, again absolute temperature, which is in Kelvin. Now if we're thinking about this in terms of unit analysis, because we want to have an expectation of what the answer is going to be before we plug it into our calculators, then we want to make sure that we've set it up in the correct way first. So let's make sure I didn't make an algebra mistake first. So my kilopascals will divide out with the kilopascals in my unit on R. My liters will divide out. My Kelvin will be dividing out here. And now I'll be left with a per mole, which flips it back to the top. So I'm going to be left with units of moles, which is what I'm looking for, because that answers the question of how many moles of gas particles there are. So that's good. My setup is okay. Now I'm looking to see sig fig wise, it looks like I have 3 in everything, so I'm going to be rounding my answer to 3 significant figures. And when I plug this in, I get 2.04 times 10 to the negative third mole. And again, scientific notation for clarity of significant figures there. Okay, so algebraically and mathematically, PIV-nRT isn't that challenging. The trickiest part is really making sure that you have your units straight, making sure you're doing the right conversions so that everything divides out correctly once you plug and chug through your equation there. Now, I keep saying ideal gas, and I want to speak to that a little bit more, because if I'm talking about an ideal gas, that must mean that there are non-ideal gases. So let's talk about why it's the ideal gas law. It's ideal because we have to make some assumptions about gases in order to use PV equals nRT. And these assumptions look like big assumptions, but we're going to talk about them here. Because assumption number 1 is that the gas particles have no volume, which we know isn't true, because anything that has mass and is made up of subatomic particles is going to take up some amount of space. But we're assuming that that amount of space is negligible compared to the container that it's in. So when we're talking about a gas here and we're using PivNert, we are assuming that V, our volume, is really just the volume of the container that it's in. If we start to factor in the volume of individual gas particles, then that's going to change the overall space of the container, right? Because we have to factor in the total number of them and the volume of them based on their chemical identity. And so we have to kind of, it gets pretty complicated pretty quickly. And I will do a video on real gases later on. So check that out. You can check out the real gas video and compare it to these assumptions that we make with PivNert. The second one that you have to make, the second assumption that you have to make, is that there's no attractive or repulsive forces that exist between the particles. And the reason that that's important, it's going to impact the pressure. We said that the pressure here is, for gases, is the movement of the gas particles and the collisions with the sides of the walls of the container. And so because of those collisions, then that causes this feeling of pressure for these gases. If I have attractive forces that are causing particles to stick to each other or to repel each other, then that's going to change our understanding of the movement of gases. It's going to change the way that they collide with the sides of the walls, which has an impact on this pressure piece to it. So when we talk about real gases, then we're going to have to factor in that pressure bit as well. So we really are making assumptions about those two bits of PivNert, the P and the V part. We have to make some assumptions about. Now again, that sounds huge. That sounds like a big thing that we're assuming. Well, when will we ever be able to use PivNert? Well, it works most of the time. It really means that it works best at low to moderate pressures. Meaning pressures that we're under most conditions most of the time. So, you know, atmospheric pressure, if we're working in a laboratory and we're not under vacuum or we're not under some kind of crazy high pressures, then PivNert's going to work just fine. And then also temperatures that aren't too low. And the reason for that one is when you start to decrease the temperature, so if I'm starting to move towards something like absolute zero where all motion ceases, then we slow down the movement of these particles. That's going to allow them to move around a little bit more or interact a little bit more with each other. So not move around a little bit more like speed up, but interact with each other a little bit more in ways that they wouldn't when they're all zipping around and moving under normal kind of temperatures. But as soon as we slow them down, then that attraction and interaction with other particles has more potential to increase. And that's going to cause things to clump up a little bit more, which is going to cause things to have more volume. So there's just kind of a lot of different impacts there. So low to moderate pressures and not crazy low temperatures, then you can use PivNert just fine. So there's a lot of conditions that PivNert works, and we can make these assumptions. Because gas particles are just so teeny tiny, they don't interact with each other all that much. They don't have a lot of attractive forces, and so therefore we can make these assumptions and then use the ideal gas law. It's a lot easier than the real gas law. The real gas law isn't that much more complicated in terms of the math. You just have to make sure that you factor things in, and you have to look things up a little bit more based on the chemical identity. So speaking of chemical identity, then things you wouldn't be able to use PivNert for, you'd have to think about bigger things and things that are more polar, because that's going to cause these assumptions to be invalid. So larger molecules with a greater amount of polarity are not going to be ideal. If you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again about gases very soon.